Good morning, good afternoon, good evening, depending on where you are. My name is Fernando Gont. I'm Director of Information Security at Juno, and I will be doing a presentation on operational implications of IPv6 packets with extension headers. Let's start with an introduction to the topic of IPv6 extension headers. Essentially, IPv6 has changed the structure of IP packets. And if you look at a sample IPv6 packet, you can see that the structure of the packet follows like a linked list type of structure, where you have a mandatory IPv6 header. Then you have a variable number of extension headers, and then as the last header, you have the upper protocol, payload or header. Essentially, the idea here is that rather than having or that including the possible options in the IPv6 header itself, like in the same way that it is done for IPv4, what we do in IPv6 is to have a fixed length IPv6 header, and if we need to introduce any kind of options, we will introduce these options via extension headers that are inserted, if you wish, in between the base IPv6 header and the upper layer protocol. Okay. So this is a very general, structure of the packets, and obviously the benefit, if you wish, is that there is no practical or there's no theoretical limit when it comes to the number of options that you could possibly include. Because if you need more options, you add more extension headers in between, and you can support as many options as you might want to support. Now, what's the problem? What's the basic problem with this basic structure? The problem is that if for some reason you wanted to process layer 4 information, the only way that you have to actually access that information is to process each of the headers at a time, jumping from one header to the next header, and so on, until you get to the upper layer protocol. There's nothing like a pointer to the upper layer protocol header that would allow you to skip all the options and jump right into the upper layer protocol. So in this example, for example, in this sample packet where we have the basic IPv6 header, and then we have a number of extension headers in between, and then a TCP header. If we had some device that for some reason needed to obtain TCP information, it would have to start processing the IPv6 header. Then it would jump into the next header, which in this case it's a hop by hop options extension header. Then it would look at the length of the header, and based on that, it would jump to the next header, etc., etc. Now, there are a couple of problems, as you might expect, that are associated with these kind of processing. The first one is that the structure of the packet is of variable length, and there are a number of architectures for which this is not really friendly. So the headers can be at any place in the packet, because all of the headers are of variable length. So this is not friendly with a number of architectures. On the other hand, hardware architectures, of course, I'm referring to. On the other hand, if the packets were being processed by a general purpose CPU, if you wish, then that of having to jump from one header to another, it's something that is going to have an impact, for example, on the CPU consumption. Okay, so that's one part of the problem. What is the other part of the problem? When you look at architectures that, for example, implement the packet processing, in hardware, what they typically do is that they copy, a part of the packet, from the very beginning, and a part of that packet into a fast memory, such that they can essentially implement any kind of operations that they might need to operate using that fast memory. Okay, the idea is that you want to copy a piece of the packet that contains all the necessary information, but no more than that, because obviously, that would require, like larger memories, and that would increase the cost. So obviously there is an implicit trade-off on how many bytes you are going to copy into that kind of fast memory. And if you look at let's say real router implementations, you can find values such as, for example, 64, 128 bytes, 256 bytes, meaning that for all of these devices, they somehow imply that all the information that you might need to process a packet, that means the whole IPv6 header chain, needs to be or is going to be within those first 64 bytes, 128 bytes, or 256 bytes, if you wish. Okay? Now, what happens if that information is not there? Well, you cannot do the fast processing of the packets that you would otherwise do, and you might need to make a decision in that case regarding what to do with the packet. Now, related issue with this topic of processing packets is that many people, when you describe all the work that a device needs to do to spot the layer 4 information, normally many people will come back to you and say, well, but if it's, for example, a network device, why does the device even need to access layer 4 information? At the end of the day, aren't those just layer 3 devices that should be able to process a packet with forward the packet just by looking at the, say, IP addresses? Well, yeah, in theory, in some cases they might be right, but in practice, when you look at real deployments, there are a number of reasons for which a device, let's call them middle boxes, just so that we don't need to focus on a router, a firewall, an IDS, or any kind of specific device. There are a number of reasons for which these devices might need to look into layer 4 information. And let's briefly describe some of these reasons. First one is to enforce infrastructure ACLs, okay? So you might have your network infrastructure and you want to essentially implement ACLs to protect your own infrastructure. That means that you might allow traffic to some of your devices for specific protocols, but not for others. And obviously, the only way in which you can, tell, which protocol you allow and which protocol you don't is by looking at the layer 4 information. Typically, the well-known port of the service that you want to allow or filter. So that's one of the reasons. Another of the reasons is for DDoS management and customer requests for filtering. So let's consider the scenario in which, for example, you have a client. And let's say your client has a port that is open that for some reason they are unable to filter, or they think that they are unable to filter. So they require you as an operator to essentially filter that port for them. So that means that before you actually forward your packets to your client, you need to tell which of the packets you're going to forward or not based on the service that is being used, based on the destination port, for example, destination TCP port, destination UDP port. That obviously requires processing the entire IPv6 header chain and looking at the layer 4 information. For DDoS management, that's kind of like similar. So you might have traffic, coming from certain addresses, and the DDoS traffic is associated with a specific service, for example. And to the extent that is possible, you like to, drop packets that you assume are part of the DDoS attack, but not traffic that seems to be benign. Seems to be valid, legitimate, okay? Again, in that kind of scenario, what you need to do is not only look at the IP addresses, but also at the transport protocol ports, which require any device that is processing the packets to process the entire IPv6 header chain to get to the upper layer protocol. Other reasons for which a middle box, a network device, might need to look into layer 4 information. For example, when you have ECMP or hash-based load sharing, typically what you try to do, the situation that you have, the scenario that you have is that you have a network device and you have multiple links over which you could possibly forward packets. Okay, so what you want to do, normally is to share the load among all those links. Okay, and you could possibly share the load by just sending packets to one link or the other round robin. But the problem with that, with that approach for load sharing is that, forwarding or deciding they're going, link round robin will normally lead to renumbering events that are not nice for the transport protocols, and eventually, has an impact, a negative impact on the user experience. So what you normally want to do is to forward all of the packets that correspond to the same flow over the same link. And, as you might expect, one of the typical or traditional ways to do that is to compute a hash over a number of parameters, such as, the IP addresses involved and the transport protocol ports involved. Meaning, again, that in order to compute that hash, you need to obtain the layer 4 information, and in order to obtain the layer 4 information, you need to process the entire IPv6 header chain. Other, you could say, more obvious scenarios or requirements for accessing layer 4 information is firewalling. Obviously, in the most common case, you implement and enforce firewall rules, at least by looking at the IP addresses and transport protocol port numbers involved. So that will obviously require the device to access the layer 4 information. And last but not least, you can also have scenarios where you're using an IDS or an IPS, and these devices obviously typically they look not only at layer 4, but sometimes to the extent that is possible, they even try to look at application layer information. Again, this requires that you access at least layer 4 information, meaning that you need to process the entire IPv6 header chain. Now, you might wonder, okay, what will happen if for some reason a device needs to process a packet, needs to access layer 4 information to process the packet, but for some reason is unable to access that layer 4 information? Think about, for example, the two scenarios that I described before, like limits, for example, on CPU usage, or limits on the size of the memory, fast memory that is employed for packet processing. Well, in those scenarios, there are essentially two options. One option is to, or basically three options, if you wish. One is to just, forward the packet without looking at the layer 4 information, which, in many cases, it doesn't make any sense at all. The second option is to stop the packet, and not process it at all. And the possible third option would be to try to process the packet in software, which, as you might expect, is a no-go. You don't want to be, throwing packets to your, device CPU, for the CPU to process it. So what happens in, many cases is that, operators configure devices such that when they cannot access the information that they require to properly process the packets, they drop the corresponding packets. As I mentioned before, we have essentially two different kinds of limits that you will see in practice. So you will see devices that enforce limits or that have implicit limits on the number of headers that they are able to process. So you might see that devices that if you include a single extension header in a packet, the packet will be forwarded and things will work as expected. But if you include, let's say, over 8 or over 16 extension headers, then the corresponding IPv6 packet will get dropped. On the other hand, as I mentioned before, there's also a limit associated with the length of the IPv6. So it's not about in this case, we're not talking about the number of extension headers, but about the length of the extension header itself. For example, it could be the result of having a single extension header, so just one extension header, but of, let's say, 1,000 or 2,000 bytes, okay? So there are these two limits in place. And when you look at, different kind of devices, you might see one in place or the other in place, or in some cases, both of them in place. These are the limits that, when hit, will typically result in the packets, being dropped. A few years ago, we had a meeting called the IPv6 Hackers Meeting, where we have a number of presentations quite interesting. And one of the presentations that we had at the time was an assessment presented by Eldad Sack, where one of the things that he tried to present was what was the performance of network devices. On one hand, when they have IPv4 only traffic, IPv6 only traffic, or mixed IPv6 and IPv4 traffic, but also Eldad had presented measurements of the performance of different network devices when the IPv6 traffic that they were processing, the traffic included IPv6 extension headers. Okay. So in this slide, essentially, we have a summary of the measurements that Eldad did for a specific device, where you have what's the the throughput when you have IPv6 traffic without extension headers, and what's the throughput when or the loss in throughput when the traffic incorporate extension headers. So this this is like a data point which shows you that the extension headers have a concrete impact on real world network devices. And you, as an operator, when faced with these kind of situations, you might need to make a choice as to whether it's okay for you to deal with these, for example, performance implications, or this is actually not acceptable at all, and you might need to essentially drop packets that employ IPv6 extension headers. So far, what we have seen essentially is the impact that extension headers have on, for the most part, the performance of devices, of network devices, which obviously at times that also has has implications on security, because if the performance is very negatively impacted, that can lead to a denial of service situation. But let's dig a little bit more into the security implications of IPv6 extension headers. And I think that the best and easiest way to provide a summary or a data point is that if you go and look at the vulnerability database and you search for IPv6 extension headers, then you might get all of these advisories. And this is a search that I did few months ago. It's very likely that if you redo this search right now, you will get even more of this. And what I'm trying to summarize here is that for a single year, like in this slide, we have vulnerabilities that were published during 2020. You have multiple vulnerabilities for different kinds of devices from different vendors, where essentially the vulnerability has to do with the devices, with the affected devices not being able to gracefully handle malformed IPv6 packets that include extension headers. To put things in a different way, it's 2021, and we still have a lot of devices that cannot properly process, packets that include IPv6 extension headers. So what does this mean? If you are an operator, so this is a data point that might also influence your decision regarding whether, to allow these packets, into or through your network or not. And if you don't have a very good use case for, the extension headers, well, probably by looking at, these numbers, it's very likely that your decision might be to just drop packets that contain extension headers. Now, you might wonder, okay, so extension headers, IPv6 extension headers have implications on the performance, the device performance. They may also have implications on security, and these two considerations might might end up causing operators to decide just to drop packets with extension headers in their networks. So how often does this happen? How often, or what's the data, or what are the stats regarding how often operators drop packets with extension headers? So these are measurements that I perform for Alexa's top 1 million domain names, and what I try to do here is to measure for different kinds of endpoints. In some cases, they were web servers. In other cases, mail servers. In other, name servers. And for different types of extension headers, in this case, we have destination options of 8 bytes, hop by hop options of 8 bytes, and a fragment header in this case of about 512 bytes. What's the drop rate? And as you may see from this slide, the drop rate, depending on the type of service and the type of header, is anywhere between 10 and 50%. Okay, this tells you a little bit about how reliable extension headers are nowadays on the deployed IPv6 internet. So. Your conclusions from what I have described so far might be that, okay, well, there's a little bit of a problem in there. So there's at least awareness to be done, and probably a few other things to be done. And the IETF in the last, let's say, 10 years did a little bit of the required associated work. So what are the things that we have done at the IETF associated with extension headers? The last RFC that we published on the topic has been RFC 1998, which essentially raises awareness about the operational implication of IPv6 extension headers. In other words, this RFC covers the materials that I have covered, throughout this presentation. Then we have RFC 7872, which includes real-world measurements about the extent to which packets with extension headers are dropped in the deployed IPv6 internet. If you look at RFC 8200, which is the last revision of the IPv6 standard, there's a lot of work or changes associated with extension headers. Among other things, this RFC incorporates the contents of many other RFCs, 5722, 7112, and others, which essentially had changed or modified aspects regarding how extension headers are processed. Now, an interesting thing resulting from all this work that was done on extension headers in the last revision of the IPv6 standard is that essentially a number of bugs, several bugs, were introduced in the contents of the fragmentation and reassembly section in 8200. So if you look at RFC 8200, you will find out that there is an errata 5941, which is like a multi-page errata, which essentially replaces the whole contents of fragmentation and reassembly from 8200 because it contains a number of errors. And finally, we have another RFC that was published earlier this year, RFC 8900, which essentially describes many of these things that I have covered throughout this presentation, but focusing on IP fragmentation. The title of that RFC is IP Fragmentation Considered Fragile. And, it covers both IPv4 fragmentation and IPv6 fragmentation. And, there are issues, obviously, that I'm not going to rehash here about issues associated with fragmentation, why it is harmful or undesirable, if you wish. But when it comes to the IPv6 version of fragmentation, I would say that it's a composed problem. So you have all the problems that you have from IPv4 fragmentation, and on top of that, you have the problems that are associated with extension headers, since that's how fragmentation is implemented in IPv6. So, conclusions about the materials that we have covered so far. Essentially, there are a number of challenges associated with IPv6 extension headers, and many of them, if not most or all of them, are associated with the very design and nature of IPv6 extension headers. To put things in a different way, that packet structure of having an arbitrary number of extension headers in between the base IPv6 extension, between the base IPv6 header and the upper layer protocol, it's really not friendly with many of the, for example, router architectures that we use nowadays. So that's a problem. That part of the problem is associated with the IPv6 design itself. Then there are also a number of problems or things associated with the specific implementations. Now, that aside, there's a chicken and egg problem associated with IPv6 extension headers. On one hand, you have a number of limits in implementations that essentially introduces a number of operational challenges for operators. And from the point of view of operators, if these packets are causing problems and I don't really have a good use case, then the obvious choice might be to drop those packets. Okay, so that's the situation in which we are right now. On the other hand, from the perspective of vendors, if if there's not really a good use case, and the extension headers, the IPv6 extension header feature is not really really able and well supported, there's not really much motivation to actually try to improve the support in their own products. So what I think that we have, and that we will have probably for quite some time now, is that we will be facing this chicken and egg problem, in which we will not see use cases for IPv6 extension headers because the feature is not really well supported in the deployed internet. And on the other hand, IPv6 extension headers are not going to become well supported if there's not a use case. Okay, so my take is that the usage of IPv6 extension headers is going to be limited to what is normally referred to as limited domains, meaning you use extension headers within your network, but not on the, let's say, public IPv6 internet. So that's so far for the presentation. I will be taking questions now, and besides that, the questions that you might raise, you can find in this slide my email address, and after the presentation, if you have any questions, you may also send your questions via email to me, and I will respond if possible.
Here's Fernando. Hello there. Good to see you. Thank you very much. Unfortunately, Fernando, can you hear us okay?
Yeah, perfectly.
Okay,
thank you.
We're slightly squeezing up against time. We may have time for one question. I didn't see one online as I came up, and I don't see one at the mic, so let's do this, not just to send you away immediately. I had a question of my own, if I could. Most of the talk was centered around the forwarding of packets and what the implications are with the headers. Is there anything that you see or foresee that could be a problem with the end host and their interaction with headers in terms of probably amplification or somehow they might respond? That might be a network operational problem. Or is this strictly a intermediate node issue that you focused on?
Yes, hosts are as bad as forwarding devices at processing extension headers. If you want a data point, one of the few remotely exploitable vulnerabilities in OpenBSD that was discovered in the last 20 years was based on IPv6 extension headers. So, the quality of the code is really bad, and, that has associated security implications. That's what I would say are the implications on the host side too.